computers are an excellent tool for understanding other systems. One of the great strengths, and what I think a computer really lets you do, is say, I want to write down rules and instructions and actions, and then watch them actually happen. So many things of what we observe in the world and what we try to understand, we try to come up with a model for how that system works. And it might be a nice simple model that helps represent some of the issues going on in that system, or a super complicated model. And a lot of the sciences, a lot of maybe social sciences and even humanities are trying to understand things by coming up with representations. And what a computer lets you take that representation and turn it into something where you can simulate it and you can watch that system happen. So not exactly computer science, but what's more commonly called scientific computing lets you do that. So a differential equation model that someone might come up with for weather or for a predator-prey simulation. You can say, how can I understand the interactions between these two components or agents inside a system? And then you represent that with a mathematical equation, and a computer lets you approximate that equation. It says the equation itself works as if there's a continuous world and everything can be modeled perfectly. But the computer is a discrete system, and it has to slice that system up into small time steps and let you sort of run the system and see what happens with it. So another perspective of computers that comes in is, instead of trying to model the relationships and the ways that agents influence each other, is what's more commonly known as agent-based modeling or individual modeling, where you can say there's an entity in the system. Instead of trying to talk about the interactions between the population of, well, let's talk about predator-prey models. If you're trying to talk about rabbits and foxes and how they interact. From a differential equations perspective and a continuous modeling perspective, you would say, how does the population of rabbits interact with the population of foxes? And depending on a probability of interaction and some energy resources that are going on, you can come up with an equation that relates, when there's more rabbits, there are more foxes. But when there's more foxes, there's less rabbits. So when there's less rabbits, there's less foxes. Well, now there's less foxes, so there's more rabbits. So there's this cycle that you can describe in terms of mathematical equations. And that kind of system is hard to analyze mathematically and solve completely for when they start getting more and more complicated. And it's not just rabbits and foxes, but there's also maybe mice running around, or you care about the grass, or you care about another predator. Once you throw in 4 or 5 or 6 different populations interacting, the equations get really big, and the only really way to do it is to approximate it and simulate small pieces of it. So a computer can come along, because it is a way to represent rules and equations and watch them work, can really help you see that. The other approach I was mentioning, the agent-based or individual-based models, says, well, instead of looking at the populations and how the populations merge together, what if you just look at an individual rabbit and try to talk about what it does, and an individual fox and what that fox does? And then you can create 100 rabbits and 50 foxes and set them loose in a simulated world and watch what happens as they interact. So you're no longer programming the relationships, but you're programming the behavior of the individuals. And in doing that, you start to see some other pieces of complexity that you don't see elsewhere. With the differential equations models, there are some assumptions that come into play of, you might end up with a situation where you have half a rabbit because it's a continuous number, and in a real world system, you don't have half of rabbits. There's 1 rabbit, or there's 0 rabbits, or there's 10 rabbits or 9 rabbits. You never get 9.7 rabbits. And the difference between the modeling approaches let you explore what happens when you try to really focus yourself on a discrete world, and what's happening with the individuals on a lower level. So the computer is a great assistant for exploring models that other fields come up with. Social scientists, natural scientists, chemical scientists, the ways that people try to understand the world can be represented as models, and you can plug those into a computer.